Okay, good afternoon, everyone. Am I audible? Anyone respond?
Yes, sir, you are audible.
Okay, right now. So in the morning session, we are discussing about the single loop generator. Okay, see here. So we are having the North Pole and we are having the South Pole. So the flux will be, the flux direction will be from north to south in this direction. So everywhere it will be the same. Okay. So here we have taken the 4 cases. So this will be the case 1. This is case 2, case 3, case 4. Okay. So we are observing the 4 cases here. So now here we have taken one loop. So with the 2 conductors. Okay. We taken 2 conductors. One conductor is AB, another conductor is CD. Okay. So now we join these 2 to make a closed loop, right? So 2 conductors are joined together, and now this rectangular loop we are going to place in a magnetic field here. Okay. So now let us see that here AB is there, here CD is there. Okay. So now it is placed in vertical direction, and the axis of this loop is this small AB. So with the dotted lines. Okay. So we have taken dotted lines inside this, and about this axis AB, this loop is rotating. Okay. So this loop is rotating about this axis. So this is the axis you have to consider as a shaft of your generator. Okay. Now, so when it is initially in first case, it is in vertical direction, right? So it is in vertical direction. Now it is moving in the clockwise direction. Okay. So now after 90 degrees of rotation, your loop will be placed like this. Okay. After 90 degrees of rotation, so now the complete loop will get in parallel to your flux lines. Okay. So here in the first case, your conductors are in vertical position, right? So that means this loop is in vertical position when it is moving towards the horizontal position. So that means in the second case, so you see here after 90 degrees of rotation, your conductor AB is here, your conductor CD is here. Okay. So now after another 90 degrees rotation, again your loop will be in vertical direction, but the conductor placement is reversed. If you observe these two, so here in the first case, AB is there in upside and CD is below. So but here after 180 rotation, AB is downside and CD is upper side. Okay. So still if you rotate 90 more degrees, then here you will get AB and here CD. So that means in opposite direction to the second case. Okay. So that means, so when your conductors are in vertical position, so maximum amount of flux will be linked with the conductors, and when the loop is in horizontal position to your loop, your magnetic flux, then there will be no EMF will be induced in here. Okay. See here. Initially at 0 degrees, then after 90 degrees rotation, after 180, then 210. Great.
70, sir.
We'll write here. So 270. Okay. So now here, initially, so if it is suppose if it is in this position, so then there will be no EMF will be induced in the conductors. Okay. So why? Because the flux lines and the direction of motion both are in parallel, right? Your conductor is in parallel with the magnetic flux lines. In such a case, there is no linkage of flux, so it will be 0. So then the EMF in the conductor will go on increases and reaches to maximum value. So when after 90 degrees rotation, so in vertical position here, you will get 90 degrees. Then again, if you rotate here, it will decrease, and again it will come parallel to this. So again it will be 0. Okay. So then again, so then again after 180 to 270 degrees, so it will be the current will increase in the reverse direction, and it reaches maximum value at 270 degrees. Then after 270 degrees, still if you rotate, it will decreases, and again at a 360 degrees at its initial position, it will come back to 0 degrees. Okay. So like this, the voltage is induced in the conductor. Okay. When you place a closed loop inside here, magnetic flux in each conductor, the current will be positive for 180 degrees and negative for other 180 degrees. Okay. So this is the EMF induced in the conductors, right? So which is of AC type. Okay. So EMF induced inside the conductors when they are rotating in the magnetic field. So then the induced EMF is AC only. So but here we are discussing about the DC generator. We need DC electrical energy. So DC voltage we require. How you can convert this AC into DC, right? So this AC type will be converted into DC type. So by using a commutator. So you will be having a commutator. Okay, it is a mechanical converter, right? This commutator also moving along with these conductors. Okay, on the commutator you can place the braces, and you will collect the current from the commutator. Okay, so we'll discuss these in the coming slides. So this commutator is used to convert this AC to DC. Okay, see here a single loop generator. Now if the conductor in the first half of the revolution, current flowing in the this closed loop, which is in contact with the best one, will be here. You see here in this diagram, this is the commutator, the circle one. So this is the commutator. Okay, so now here these are the brushes. Okay, so these brushes are stationary parts, and this commutator, so it will rotate along with these conductors. Okay, now if you observe, this commutator is having segments, right? One segment is A, another segment is B. Okay, so these segments A and B only they are conducting, and this part, if you see this part, so this part is not conducting here. Okay, so now while this loop is rotating, suppose if you see the first figure in the first half of the revolution, your commutator segment A is connected with the connected this side, positive side, and commutator B is connected with this side. Okay, so you are getting a first waveform like here across the loop. So then if you so initially the direction of current is in this side, here it is in this side. Okay, so here actually you have the north and south poles. Okay, so here are the same north and south poles will be there. Okay, so now conductor in the first half cycle, conductor AB is under north pole and the conductor CD is under south pole. So the direction of current and here is downside, and under south pole it is upside. Okay, so you see here this one, so this is not there, your loop will be like this. Okay, so this is the loop. Now the current through the load, if you observe, so this is flowing like this. So through this commutator and brush, it will goes to the load and it will come back to the negative brush, and then through through commutator segment B, so the closed loop will be formed. Okay, so in this direction it is flowing. Okay, so now after this loop is rotating another half, okay, another 180 degrees, then this AB will come under south pole and CD will come under the north pole, right? The current under the north pole, if you see, it will be downward, and under the south pole it will be upward as this. Okay, so now you see here also, if you observe the direction of current, so through B you are getting current like this. So if you use the commutator, you will get the current in only one direction. Okay, so that means during 0 to 180 it will be in the same direction, and 180 to 270 also it will be in the same direction. Okay, you are getting a DC voltage like this when you use the commutator here. Okay, so this is about the single loop generator. Okay, right now let us see the construction of a DC machine. So see here, it is a DC machine. So DC machine in the sense, it may be either a motor or a generator. Okay, so DC motor and DC generator, so the construction will be the same. Okay, so if you have a DC motor with you, then the same motor you can use it as a generator also. Okay, so DC motor in the sense, this input is electrical, output is mechanical. Suppose for the same machine, if you give the input as mechanical, you will get the electrical output. So a motor can be used as a generator, or generator can be used as a motor. Okay, so the construction of the DC generator, DC machine will be the same, whether it is a motor or generator. Now if you observe the cross-sectional view of your generator or motor, so this is the cross-sectional view. Okay, so cross-sectional view of DC machine here. So if you observe the main parts here, you have the yoke here and here. So this one, so this is the pole. So then on the pole you will be having field winding. So then inside you have the one armature. On the armature, so you'll be having the armature conductors or armature winding will be there. So then you have the commutator. So this commutator is represented with will be having the commutator segments. So those are represented like this. Okay, so commutator you are having. On the commutator you have the brushes. These black one are the brushes. Okay, so from the brushes only you have to collect the current outside the armature. Okay, so you can connect the external load so only through brushes here. Okay, so now here this is a DC machine in which you are having the 4 poles. Okay, so if it may be north pole, south pole, north pole, south pole, like that. Okay. See here. So the DC machine will be looking like this. So in the previous slide, we have taken the cross sectional view. So this is the side view. Okay. So here again, the parts of a DC machine is represented on the on this view. Okay. So here are the poles. As I said before, for in a DC generator, so the elements which you have, any elements. So in a DC generator, to get the voltage or EMF, so EMF will be induced only when you have a conductor and you have the flux, and between these two you must have the relative motion. Okay, these are the requirements. Okay, so for the generator, for getting the EMF to be induced, you must have the conductor or coil, and you must have the magnetic flux, and there must be some relative motion between the conductor and magnetic flux. Okay, so in DC generator, you are going to rotate the conductors, you are going to fix this magnetic flux. Okay, how you can produce this magnetic flux? How you can produce this magnetic flux? The magnetic flux will be produced either by using permanent magnets. Okay, you know the permanent magnets, or you can use the electromagnets. Okay, so either you can use the permanent magnets or you can use the electromagnets. Okay, so what do you mean by this electromagnet? You already know about the permanent magnet, right? So what about the electromagnets, right? How you can make the electromagnet, right? Now for that purpose, you take one ferromagnetic material, right? So now let us this is a steel, let us take. Okay, so steel core, right? Now on which you are going to wound the wires like this. Okay, so now if you pass the some current through this, then this bar will act as a magnet. Okay, so this bar will act as a magnet. Now it is called the electromagnet. Why? Because through by supplying the electrical energy to this, we are going to make this as a magnet. Okay, so now for this magnet, how you can identify the north pole and south pole, right? So now if you see the direction of current here, it is going on the top of your magnetic bar, right? So in another way, you can represent like this also. So inside it will go and it will come from in this way. You can wound the wire like this. Okay, so now your current is going below this magnetic bar. Okay, so now if you hold this same, suppose let us assume that you are holding this magnetic bar with your right hand, such that your curled fingers represents the direction of current. So then your thumb will represent the north pole. Okay, if you see here, if you hold this with your right hand, you hold this with your right hand. Now it is below, your curled fingers will be going below the bar, and your thumb, if you see, your thumb will be pointing this side. So this will be the north pole and this will be the south pole. Now if you hold the same bar with the right hand, now for this case your thumb will be pointing towards this. So this will be the north, this will be the south. Okay, so like that you can get the either north poles and south poles here. Okay, so depending upon this. So see here in this diagram. Okay, so now here if you observe, so this wire where you are supplying current, it should not get repeated, right? It should not so if you see here, let us assume that current is coming like this through this wire. So in this direction, okay. So through this, so suppose if you are given some voltage, DC voltage here, so current is flowing through this winding, and it will flows through all this winding and coming back here. Okay. So now if you see here at this place, your conductor, your current is above your bar. So right. So this is the pole core. On the pole core, you have wounded the wire here. Now the current direction in the this winding will be upward the pole core. Okay, this is called the pole core. So pole core, right? If you hold this if you hold this pole core with your right hand, then you can observe that. So this side is your right finger. So this will be the north pole. Okay, then after coming here, so now this wire is going inside your pole core. So if you hold this with your right hand, so then so this side you will get the north pole. So this side you will get it as a south pole. Okay. So then after coming here, so now your current is your wire you wounded the wire on the top of the pole core, and if you hold this bar with your right hand, so then you will get this as a north pole. Now after coming here, so then you will get your thumb will be in this side, so that means it will be this side will be north, so this will become south. So like that now. Okay. Okay, right. So now giving some voltage to this winding or supplying some current to this electromagnet, it is called the excitation. You remember this word. Okay, so you remember this word excitation. Okay, so to make this bar as a magnet, we are going to supply certain current through this winding. So that the supplying of this current is called the excitation. Okay, now the voltage applied is called the excitation voltage, and current is called the excitation current, and this process is called the excitation of your winding. Okay, so generally in a DC generator, these magnetic electromagnets will be used as a fixed terminals. Okay, see here. So these are the poles. On the pole, some winding is wounded here. Okay, so this is called the electromagnet. DC machine. So the first one is the yoke here. Okay, so this body of the your DC generator, you can call it as the yoke. Okay, so right, so yoke or body of your machine or DC machine. So the outer frame of your DC machine, you can call it as a yoke, and this core yoke is made up of cast iron or steel. Okay, so this yoke will provide the mechanical strength to the whole assembly of the DC machine, and it carries the magnetic flux also, so which is produced by the field winding. Okay, so the field winding is nothing but the winding which is wounded on this pole course. Okay, now this winding which is wound on the pole course, so this winding is called the field winding. Okay, already we represented here. Okay, this winding is called the field winding, or you can also call it as excitation winding. Okay, and you also have thought about C, D, G, F, C. But what is this C? It is A, B, E, G, F, C. What is it? Where do we start here? Right. So now this outer part of the DC machine is called the yoke or body of the DC machine, and the purpose of this yoke or body of the machine is that it will give the mechanical strength to the whole assembly. and it also provides the path for the magnetic flux which is produced by the this electromagnets, right? So which is the field winding, you can also say. Okay, so then you have the poles and pole shoes. Okay, if you observe the pole here, so here in the circuit, okay, so now this part, right? So this part is called the pole. So this entire thing is a one pole. So like this, you total you are having the 4 poles here. Okay, so now up to this, the horizontal up to this, you can call it as this as a pole core. Now here after this, you are having one curvature here like this. If you observe the each pole, you are having the curvature like this. Okay, so now this is called the pole shoe. Okay, so then what is the purpose of these poles and pole shoes here? Okay, see here in this diagram also they are represented. Okay, so this one is called the pole shoe and this one is called the pole core. Okay, on the pole core only we generally wound the field winding. Okay, to make this as a magnetic pole, you have to supply some current to this winding only. Okay, these are called the electromagnets, right? So generally if you see these poles, so poles are joined to the yoke. So with the help of the bolts or welding, so right, so you will be having the bolts like this. With these bolts you are going to attach these poles with the yoke. Okay, in this diagram also we are represented. Okay, so this pole is attached to your yoke here through either winding either welding or through bolts. Okay, so generally what is the purpose of these poles? So these poles will carry the field winding. Okay, so you see here in this picture, so this pole is carrying the field winding and pole shoes are fastened them. Okay, so this pole shoe, the purpose of this pole shoe is that the magnetic flux produced by this field winding will be uniformly distributed across the armature. Okay, so the pole shoe purpose, if you see, so they will act as a support for the magnetic field, right? This pole shoe will act as a support for the this magnetic field winding. Also it will spread the flux in the air gap uniformly. Okay, so the purpose of this curvature is that it will spread the flux uniformly through the air gap. I'm using it. Lab క్లాస్ లో ఉన్నా అంటే ఇది క్లాస్ అంటే ల్యాబ్ లో క్లాస్ చెప్తున్నా. నేను చెప్తున్నా. Right, ma. The next part of the DC machine is the field winding. You already know that this field winding will be wound on the pole core. Okay, so on the pole core you have the field winding. You see here, so this winding, so which is called the field winding. So you can also call the field winding as a excitation winding also. Okay, so the magnetic flux will be produced by this field winding only. So whenever it is possible, whenever it passes some current. Okay, so generally this field winding is made up of copper. So copper material is used for these field windings, and they are placed on the pole and are connected in series. Okay, so if you see here each pole, so each pole is having the some part of the field winding. Okay, and all the field windings in all pole cores, if you observe, those are connected in series. Okay, so the field coils are placed on the each pole and are connected in series. Okay, so they are wound in such a way that when energized, right, when energized in the sense when you supply the some electrical energy to or some voltage to this winding, so they form the alternate north and south poles here. So that means, so this, if it is north pole, this will become the south pole, and this will become the north pole, and this will become the south pole, like that. Okay. So whenever you energize the field winding, so then alternate north pole and south poles will be created here. Okay, that means they will act as a magnets, and they will spread the flux here through the air gap. Okay, they will spread the flux here. Now here you are having the armature core inside this air gap. So on the this shaft. Okay, so what is this armature core? Let us see. Okay, armature core. So this armature core is also called as the rotor of a DC machine. Rotor of a DC machine and armature core both are the same in case of a DC machine. And this armature core will be in cylindrical shape, right? It will be in cylindrical shape, and it will be having some slots on the periphery of your armature. Okay, so see here. So this is the total armature. Okay, so and this armature will be having the laminations. Okay, one lamination is shown here in this picture. Okay, such a type of laminations are connected in series, so that it will be forming a cylindrical armature like this. Okay, so the purpose of this lamination is to reduce the eddy current. We will discuss what are the different types of losses in this emission. In such a case, we'll get this. Okay, so generally you remember that this armature core is a laminated core. So laminated core in the sense we are not going to use the solid core. So we will be having laminations, and those laminations were staggered together to form this cylindrical shape armature core. And this material, if you observe, so the material to make this armature core is the steel only. Okay, generally steel material only we can use the use for the manufacturing of this armature core. And this armature is, as I already told, it is built up of a thin laminations. So the laminations also are of very thin laminations, and this thin laminations will reduce the eddy currents, right? Eddy current losses here. So what is this eddy current losses? We will discuss while discussing the different types of losses in the DC machine. And also this armature core is provided with some ducts here. If you observe, you are having some ducts on the armature core. What is the purpose of this this ducts here? Through these ducts, the air will flow and they will act as a cooling media. Okay, so for cooling purpose only we are using these ducts. And generally this armature will be connected to the shaft. See here, you are having one hole in the middle. Through the in this hole only we will connect a shaft here. Okay, so this is about the armature core. Okay, and this armature is core is also called it as a rotor of a DC machine, and the shape of the armature core will be in cylindrical shape. And for manufacturing this armature core, we are going to use the laminations. Okay, this lamination will reduce the eddy current losses. Now this armature core is having slots like this. Okay, so on the periphery it is having many number of slots will be there. Okay, on these slots only we are going to place the conductors. Okay, so those conductors are called the armature conductors, or you can even call it as the armature winding. Okay, so armature winding, next part is the armature winding. So this armature winding is made up of a copper. Okay, so armature winding is also copper. Field winding and armature winding both are copper only here. Okay, and this armature winding will be placed in the armature slots. Sometimes instead of winding you can even use the conductors. Conductors are bars. Class లో ఇలా ఇస్తాము. Okay, ma. So the armature conductors, if you observe, these armature conductors are placed on these slots. Okay, each bar is placed in these slots only. Now,
right? Graph is the resolution factor nodes management and so in the previous
okay, right? So in the slots of your armature, you can place the armature winding or armature conductors, and these armature winding or armature conductors will be made up of the copper material. Okay, so this copper material will wound inside the slots of your armature. Okay, and these armature conductors are also insulated from each other. So while placing these armature conductors, they will be insulated. So okay, so this armature winding also can be wound in two methods. One method is called the lap winding, and another method is called the wave winding. Okay, so you can use the layers also, like double layer lap winding, double layer wave windings. Okay, so double layer winding means that the armature slot will carry the two different coils. Okay, so if you observe the armature slots, okay, so inside the armature slots you can place the conductors, right? Now if you place only one conductor, it is called a single layer conductor. Instead of that, if you place the two conductors, then you can call it as a double layer conductor. Okay, so then what is lap winding and what is other wave winding, we will see further in the coming slides.
and capacitors when lines second point,
Right. So next part of the DC machine is the commutator and brushes. Okay, so commutator is the main important part in the DC machine, right? So I already told that the purpose of this commutator is to convert the AC energy which is produced inside the conductor to DC. Okay, so we discussed about the single loop generator. In single loop generator, if you observe, the current or voltage which is induced in the coil is of AC type. Okay, so here see, you will be having an AC type inside the conductor, armature conductors. Inside you will be having the AC. Now this AC will be converted into DC by using this commutator. Okay, so this commutator will be having the copper segments. Okay, so now on the top of this commutator, you will be generally placing the brushes, right? The purpose of brushes is to collect the current from the commutator. Okay, see here, the physical connection to the armature winding is made through commutator and brush arrangement. The function of the commutator is commutator in a DC generator is to collect the current generated in the armature conductors, whereas in case of a DC motor, commutator helps to provide the current to the armature. Okay, you see this point here. Okay, so now as I said before, this DC machine can be used as either motor or generator. Suppose if you are using this as a DC motor, right? So when you are using this machine as a DC motor, in such a case, the commutator collects the current. Sorry, commutator will supply the current to the armatures through brushes. Okay, externally we supply some voltage to your brushes, right? Now through brushes and commutator segments, the current will be going to the commutator segments. So in case of DC generator, so electrical energy will be generated inside the armature conductors. Now from the armature current, the generated electrical energy will come to the commutator, and then from commutator we can collect the current to we can supply the current to the load through the brushes. Okay. And these braces are generally made from either carbon or graphite material. So for the braces, we'll use the carbon or graphite, and for the commutator, this commutator will be having the segments, right? So that segments are made up of copper. Okay. So this is about the construction of DC machine.
So if you have a direction, set direction, right? And you should also have this labeling.
Okay. As I said before, the armature winding of a DC machine of two types. Okay. One is lap winding, another is wave winding. Okay. So what is this lap winding and what is this wave winding? Let us see.
Even represent them these three topologically equivalent, right? So can you draw it? This is not only the way you represent.
Okay. So the first one, lap winding of a DC machine, right? In the lap winding, the completing end of one coil is connected to the commutator segment and to the start end of the adjacent coil, so located under the same pole. Okay. So now if you're having the different coils in a DC armature winding, so let us see two coils here. Coil 1, coil 2 we are taking. So in case of lap winding, so the completing end of one coil, that means this end, right? So if you take one coil, so it will be generally having two conductors. This is one conductor and this is another conductor. So this conductor is called the start end, and this end is called the completing end. Okay. So for another coil, so this is the start and this is the end, like that. Okay. So every coil will be having, that means current coming here and leaves here, current comes here and leaves here, like that. Okay. The conductor where the current is coming inside the coil, it is called the starting point, starting terminal, right? So where it is leaving, it is called the end, completing end or end of the coil. Okay. So now in case of lap winding, this completing end, so completing end of one coil is connected to the commutator segment. Okay. So commutator, so these coils, you will be having the commutator segments here. So commutator segments will be like this. Okay. Here like this you will be having. Now this completing end will be connected with the one commutator segment and to the start end of the adjacent coil. Okay. So start end of the adjacent coil, like this you will connect. Okay. And which is under the same pole. Okay. If you observe the poles here. Okay. So it will this commutator will be at the same pole. So similarly, all coils are connected like this. Okay. So if you are having, let us take three coils here. Okay. And here you have the commutator segments. Okay. So now the completing end of this is coil 1, coil 2, coil 3. Okay. The completing end of coil 1 and start end of the coil 2 both are connected together and is connected to the one commutator segment. Similarly, the completing end of the second coil and starting end of this third coil both are connected together and is connected to the commutator segment, which is under the same pole, like this. So the winding will be connected. Such type of winding is called the wave winding. So now this sorry, not wave winding, this is the lap winding. Sorry. So this is the lap winding. Okay. So in lap winding, successive coils will overlap each other. Okay. If you see here this in this figure, so this coil and this coil, if you see, these two coils will overlap. So because of this reason, this winding is called a lap winding, as they are overlapping each other. So then, overlay. Right. So lap winding is over. Now if you see the wave winding here, okay. So in wave winding, the coils which carry the current in one direction are connected in series, and the currents carrying in opposite direction are connected in another series, and they are together connected in parallel. Okay. So if you see here, you may be having the poles, right? North poles and south pole. When the conductor is under one pole, it will be the direction of current will be in one direction. It is another pole, it will the direction will be in another direction, right? So now in the winding, you have to observe that in each coil, the direction of current is current how it was. Okay. So now depending upon if the same current is flowing the two conductors, then you have to connect them in series. So let's see here in the wave winding, the coils which are carrying the current in one direction are connected in one series circuit, and the carrying current in the opposite direction are connected in another series circuit. Okay, so now these two are connected in parallel here. Okay, so after passing one round of the armature, the winding falls in a slot to the left side of the starting point. So then it is called the retrogressive lap wave winding. So suppose if it fails to if it fails one slot to the right, okay, then it is called the progressive winding. So see here, so progressive wave winding and retrogressive wave winding here. So now here, if you observe this winding, so now this here, it is the right to the first conductor. So first conductor in the sense this conductor. Okay. So now here, if you see here, now this point is it is having it is left to the first coil. So first coil is this one. So this one, sorry. Okay. So for this coil, it is to the left. So like that, if you are having, if it is having a right side, the winding, my winding may be a progressive winding, and if it is for the right side, sorry, left side, it is a retrogressive winding. Okay. So generally in wave winding, if you observe, the end of the coil 1 and the starting of the coil 2, so these are connected together, and these two are under the different poles. Okay. So in wave winding, the starting end and both are in the same pole.
Yeah. So you can.
Okay. So in lap winding, how we are connected? After taking two coils, so start end and completing end of one coil is connected with the starting end of another coil, right? And those two are on the same pole. Okay, so they are located under the same pole. So, but in case of wave winding, those are at different poles here.
3, 4, 5, 6. So between 1 and 2
ఇది ఏందో ఒకసారి ఎరేజ్ అవుతుంది ఒకసారి
4 and 5, 3 and 5, 5 and 6. 3 and 6 have
right. See here. So this end of the coil is under north pole, and start of the coil is under the north pole. Okay, so these two coils are under the different poles in wave winding. So, but if you observe them in the wave lap winding, in lap winding they will be under the same pole. Okay. So now if you observe the simplex and duplex or multiplex windings. Okay, in simplex lap winding, so the connection of the winding is such that there are as many paths as the which are in parallel. Okay, so on the parallel paths will be same as the number of poles. Suppose if you're having the two poles, two number of parallel paths will be there. Okay, so whereas for duplex, you will be having number of parallel paths which are equal to the twice that of the poles. Okay, in a duplex winding. So if you are having two poles, so 2 times of these 2 poles. Okay, so in a triplex winding, 3 times of this number of poles. If you are having 4 number of poles, 3 times of these poles. Okay, like that the windings will be connected. So because of that reason only, so that this lap winding is, you can also call it as a multiple winding or parallel winding. Okay, so when they are connected in parallel, so what will be the advantage? The current will be increased. Okay, so output current will be very high. Now, some important notes for the lap winding is that if you observe the number of parallel paths in lap winding, so this value will be equal to m into p. So m is called the multiplicity and p is called the number of poles. Okay, so what is m here? Multiplicity. So suppose if you are having 6 poles here and your winding is a duplex lap winding, duplex in the sense multiplicity will be m will be 2. Okay, so in such a case, the winding will be given how many number of parallel paths? 2 into 6, total 12 parallel paths will be there. That means your winding will be having 12 parallel paths like this. Like this, 12 parallel paths will be there. Okay, so now if your current from the armature is IA, total current is IA. Now this total armature current will be divided across these paths. So that means if you are having m number of p number of paths, current will be IA by p. So in each path, the current will be equally divided. Okay, so the total number of poles are equal to the total number of brushes here in the lap winding. If how many number of poles are there, so those many number of brushes you have to take in the lap winding. Okay, and IA is the total armature current. In such a case, the current in each parallel path will be IA by P. And this lap winding will be used for low voltages and high current machine. So why? Because here the windings are in parallel. So in parallel circuit, current will be more and voltage will be less. So this type of winding will be used for low voltage and high current DC machines. Okay, so now if you observe the notes for wave winding. Okay, so in wave winding, so you will be generally having only 2m parallel paths. Okay, so m here is the multiplicity factor. Okay, so it doesn't depend upon the number of poles here. Okay, so in case of lap winding, number of parallel paths is mp. Okay, depending upon the poles, this number of parallel paths will be increasing or decreasing. So, but in case of wave winding, so this parallel paths will be fixed, right? So for a simplex winding, you will be having only 2 parallel paths, and if you are having a duplex winding, so then 2 times of 2, 4 will be having. For a triplex winding, you will be having 6 parallel paths like this. Okay, and the number of brushes required here will be only 2, irrespective of the number of poles. But in case of lap winding, so number of brushes will be equal to the number of poles. Okay, and if IA is the total current flowing in the armature, right? As I already told, here you will be having only 2 parallel paths for a simple wave winding, right? So now if IA is your total armature current, so this will be divided between these two only. So IA by 2 here, IA by 2 here. So current in each path will be IA by 2 always. Why? Because there will be only 2 paths are there for a simplex winding. Okay. And also since the wave winding is a series winding, so generally it is used for the high voltage and for low current machine. Okay. So lap winding is used for high current or low voltage. So in such a case, you can use the lap winding. For wave winding, you will be having high voltage high and current will be low. Okay, so this is about the windings of your DC machine. Okay, we discussed about the parts of DC machine and windings of DC machine. And in the next class tomorrow, we will discuss about the
number of links, right? See,
types of DC generators, and what is the EMF equation, and what are the losses, and how we can calculate the efficiency. So till now, if you are having any doubts, you can ask me.
suppose this is the principle. This is the graph here. Okay, please, numerous, we can use numerous. 1, 2, 3. There is we have only 2 branches A and C. We can also draw using branches A and B. Right? We can even use. We can draw B and D, A, B, A, C. Right? Similar examples here. For this diagram or for this graph, and it's a full oriented graph, fundamental oriented graph. So what is the difference is drawing a tree? You can use any method here, right? G and G. Without form. What is the condition now? It should consist all the nodes. You should not have any closed path. No formula. Just by direct inspection. Once you directly see the once you see the graph,
హలో ఏంటి మా చాటింగ్ అది మీ ఇష్టం వచ్చినట్లు
you can directly write draw the see each of these are unique, right? All these things which are you can consider any of them. Proper say come to make each of this is about three types. Twigs. So what do we twigs means? A connected circle having almost and branches of the tree or politics. Now,
సో you rename your name with roll number everyone. సో రోల్ నెంబర్స్ పెట్టండి మా నేమ్ తీసేసి. సో రోల్ నెంబర్స్ లేకపోతే ఇంకా నేను వాళ్ళని రిమూవ్ చేసేస్తాను. చేంజ్ యువర్ నేమ్ టు రోల్ నెంబర్. Do it fast, so you will also not get the attendance. So I'm keeping them in the waiting room until they change their name to roll number.
but this how many directions of graph here will given any pair of nodes, how many directions of graph here will be pair of nodes. And this is considered this was pair of. Suppose if I say this is what it is say.
Okay, right now.
Now between pair of nodes is pair.
So let us see now the laboratory experiment in MATLAB. So in the last lab, we discussed about how to drag and drop the different components, how to connect the circuit, and how you can connect the ammeter and voltmeter, and how you can observe the voltage values and current values. Okay, so let us now see the nodal analysis or mesh analysis by using MATLAB. Okay, so you open the MATLAB.
It is the number of Have any nodes, number of branches.
Okay. So let us see the MATLAB.
See, what is the common thing between all these trees? You can see 3 branches in all.
So once go to the search box.
They have a number of
So then type MATLAB and click on this MATLAB app, and you will open like this. So wait for some time. So then you will get one window.
Have 3 nodes. In 3 you have only 2 branches, 2 peaks. Minus 3 does not contain any loops. That's what the basic condition is. You know, loops. So every graph, every connected graph is one. Every connected graph.
Update అవుతుందా సంది?
One.
చేసిరా?
And the minimum internal nodes. Minimum internal nodes are 2. What is the internal nodes?
Right. So after getting this MATLAB window, you go to the Simulink. Okay, here you have the Simulink. See here, you have the Simulink here. You click on the Simulink. So you will get another window.
Right. Now let us see example here. For a graph shown here, this is a good coordinate. How many nodes we have here? 4. How many nodes we have here? The branches is here. I use as its here for drawing that. There are numerous ways of drawing this, but we are interested to say that we are interested here in drawing this tree, right? Suppose say.
Okay, right. So after clicking on the Simulink, you will get one window, so which is looking like this. Now here you have to select the blank model.
In this tree, what are the elements we consider?
So after opening the blank model, you will get a untitled Simulink script file, Simulink file. So where you can connect your circuit.
And what are the elements that are, or what are the branches that are involved in drawing some type of tree? We call them as trees. So A, B, C, or A, C, E, or called as trees. Now, this doesn't complete the graph. So what should be done now is, since if I use a solid line here, it forms a closed loop. So what should we do is, we use some links, right? We use some links, some branches as links, like shown here, B, B, F. So what do you call them as?
So here, see here, untitled Simulink. So this is the working space where you need to connect your circuit. Okay. So today we are going to verify the mesh analysis and nodal analysis. You save this file here. Save with some name here. So mesh I'm saving.
The delay is because of your friends who want to join the platform. So AC is called as peaks, and branches P, F, and as links. Like see from see that 3 branches. and n nodes, the number of reads were selected is -1, and the number of reads with respect to this tree is b minus n plus 1.
Okay, right. So then you go to the Simulink library. So here you have the library. You click on the Simulink library. So now you got the Simulink library here. So in this Simulink library, you go to the Simscape. So under this, you go to the power systems. Under this, you go to the specialized technology. Under this, you go to the fundamental blocks. Now here, you go to the source and take the DC voltage source in, and you add it to the model. So you got the DC voltage source here in your model. Okay. So then after the DC voltage source, again go to the Simulink library and go to the elements and take the RLC series branch and add it to your model. So then you will get this. Now you double click on this and select only the resistance, and you can even select the value of resistance also. Okay. So this value of resistance may be 220. Okay, like this, you can take the number of right. So number of resistances you can take, and you can connect one circuit like this.
Yeah, Hemant, are you there?
So to rotate this, Control R you have to use,
You join the meeting.
and you connect this here. You rotate this and you connect here, and you connect this and this with this, and you rotate this and connect this with this, and here with this. Right. So this is your circuit. Right. As I already told before, to execute this, you must have the power key block. Right. This power key block always you have to use inside the this model. Okay. So this model power key block, you keep it aside just. Okay.
Identify trees.
Now in mesh analysis.
So what are the things you can know? Have four nodes. Definitely you can three trees or three branches or three elements or trees to write that without forming it. So these are the 7 ways or 8 ways you can take them as tree. Right? Is this okay? Up to 3 and grams. Trees. Yeah. Leaves, what are the leftover part? We are interested in drawing the tree, right? Once the trees, the rest of the tree can go as the leaves, right? For suppose this is a tree, you can use dotted line to represent it. Okay. So extra part, yeah, remaining elements you can call them as leaves.
Right. So you take the power key block and keep it aside. Now in this circuit, you have to represent your all resistors. Okay. Actually, so what are the values of resistor you have used in your lab? Actually, I don't have the idea. So I'm randomly selecting some of the resistors. So let it be 150. Let it be 100. It is 1K. This is 82. This is 47. Right. So like that. Now, so in mesh analysis, what is our purpose? You need to find out the loop currents. Okay. So now how you can find the loop currents here? Okay. So for finding the loop currents, you need to take the ammeters. Okay. So you need to connect the ammeters in the circuit. Okay, now you remove this here. So how we can form the ammeter? As I already told, you go to the Simulink library, go to measurement block, take the current measurement. Okay, now this current measurement will only measure the current. So to display the value, you have to select one display. That display is there in the sinks.
So what do you do with all these representations? Fundamentally, we need to write some matrices or else. See what
Right.
I have done with
Now,
mesh analysis.
this current measurement block with together with the display block, it will act as a ammeter. Now here you remove this circuit, and here you connect your ammeter. So plus is connected here, minus is connected here, so that it will give you the loop current I1. So to get the loop current I2, here you have to remove, and here you have to place the same current measurement block, and it is connected with some display. To get the current in loop 3, here you have to remove the circuit, and here you have to place the ammeter again. So current measurement block and display is connected like this. Okay, so now take voltage as either 10 volts or 5 volts, and you just run this. Okay, so then you will get the values of all loop currents. Okay, the loop currents will be displayed here. See here, in the first loop, 0.036 amperes of current is flowing. In the second loop, 0.0106 amperes of current is flowing. And the third loop, 0.0004 amperes of current. Okay, this current is in amperes, not in milliamps. Okay, if you want to convert this into milliamps, you have to multiply this with 1000. This is simple, verifying the mesh analysis in MATLAB. So this is the simple circuit. So you just need to connect the circuit, and you have to run the circuit. Okay, so for the same circuit, you can even apply the nodal analysis also. Okay, how you can apply the nodal analysis? I'm taking the same circuit. Okay, so here you remove the current measurement blocks. Okay, so remove the current measurement blocks,
and I of A of I j will be equal to -1. If j branch is instead.
Okay, so now the connect the circuit here as it is.
Or it will be 0 if j branch.
So now to know the nodal voltage, how many nodes are there here? Here this is one node.
I just show you the circuit and
so right, this is one node, and this is another node. The last one, ground one, is another node, right? So now the third node is taken as the ground node, where the voltage is 0 value. Now other two voltages, two nodes are the this node and this node. Here you can call it as V1, here you can call it as V2. Okay, so now to know the values of V1 and V2, you need to connect the voltmeter. So in a similar way, how you measure the current, the same procedure we will go with the voltage measurement also. Go to the measurement block and take the voltage measurement. Okay, now if voltage measurement is connected with the display, it will become a voltmeter. Okay, now this voltmeter always must be connected in parallel to the element. Now if you want the voltage at this point, so the voltage across this point is nothing but voltage across this point and ground, which is nothing but voltage across this resistance. Voltage across this node is nothing but voltage across this element. Okay, so you have to connect your voltmeter across this element, so that you will get the voltage at node 1. Okay, so if you connect the voltmeter across this element in the second element, then you will get the second node voltage.
What does representation have here?
Okay.
from one to direction of irrigation is from one to.
This is how you can connect. So if you run this, you will get the nodal voltages here in the display.
And with respect to what the element, what's the element? A. If the direction is
See here. So here the node voltage is 2.079 volts, and here the node voltage is 0.400803, I think. So 0.3 volts. Okay. So this is how you can connect the circuits to verify nodal analysis and to verify the mesh analysis.
And how much between which node it is connected between node one.
So any doubts here, ma?
But we have to get some data. So what is the positive value and what is the negative value? Since the arrow is towards and it is minus. The arrow is towards from the what is the condition for writing this fundamental factor incidence minus?
Okay, right. I'm stopping here. If you're having the doubts, or you can ask me. Still 1 hour time is there.
The branches are connected to two nodes. Any two nodes in the graph. Similarly, this element C is connected with node 1 and right. And the direction. So where will two values coming 1 and minus 1 is 1 and 2. And if you know that direction towards 4, that will be minus. So 4 is greater than minus, 1 is greater than minus. Similarly, branch B is connected between 2 and 4, and is directed towards 4. So 4 will be minus 1, node 2 will be plus 1. And the result is minus 1, and for here, 1 minus 1 is node 1. What do you call that? Fundamental incidence matrix. Is that okay? Is that okay? This is how we write an incidence matrix, right? So we call this as fundamental complete incidence. Okay. So the properties of incidence matrix are that. So when you get this incidence matrix, then this is fundamental incidence matrix. But when you get a incidence matrix, you get incidence matrix is represented with A. Incidence matrix is represented with fundamental incidence matrix. Fundamental incidence matrix of complete incidence matrix is represented with A.
See, you muted yourself.
One row is A. One row of A is divided by so some textbooks have used this notation. They will call this A as complete incidence matrix and A as incidence matrix. After we so some authors are writing this first one as incidence matrix and other as reduced incidence matrix. And most of the times I'm using this. This is one more example for this incidence matrix. Is it a planar network or non-planar? Example given here. Is it a planar network or non-planar? How do you jump to the conclusion? It's non-planar. But what I draw this from the outside. So what over here, after guys, I'm drawing stop going to this. Or all I can remove this from what happens to the drawing. It is a possible design. So what how many times we have to set up? Right. So you know that how to write this. The node branch one is so it goes to these points. All these we can write for each. So how do you write for each? Right. The direction towards V4, so V4 is what? V4 is similarly we can write for that. Now this is the reverse of that. Draw the graph transform. Give it that. You write that you let us see the here not the attendance. You have the attendance for the session from the class for last class. Yeah, please take it. Meanwhile, you try to cover. So, how many notes you have? Yeah, 5 notes, right? So, the number of rows here you have is 5. You write it as A, B, and how many branches you have?
Three hours and continuous exam.